Okay, so welcome back everyone. Let's begin today's class. Just a couple of things like in the last class we did something about modeling exercises, some modeling questions. So I also posted some material on that. So yeah, I think to get practice on these kind of modeling problems, you can go through that reference. So like people usually don't give it as a separate exercises or a separate section. So that's why it's like spanned across multiple sections. So some parts, on how to model things as a linear program, some as an integer program, and some general things. So, yeah, to get an idea of the overall framework of modeling, I think it's necessary to go through each of these sections. Okay, so just to get a sense, did any of you get a chance to go through these sections? You can answer in the chat box. So no one's got a chance to go through the questions, the material posted. Okay, so if you haven't gone through it, you should start soon, because you'll also soon get your assignments, and yeah, it's important to be able to at least start off with modeling. And you should also try some solvers, right? Like we did some problems in the last time, like max flow and vertex cover. So some formulations I showed you that. So you should also try these on some solvers like Gurobi and MATLAB. So there are like a lot of references online. Okay, so it's not very hard to start picking up, and you're all CS students, right? So it shouldn't be hard to pick up a language. And I guess you guys are all familiar with Python, right? Yes, no?
Yes, no. Yeah.
Okay, so you can check out this language Gurobi. So maybe I'll just post it on the chat box. So, this is a standard solver, and it should be available for you for free because it's an academic institution. So if you log in from your IIT Goa ID, you should be able to get access to it. So you should start, trying some of the examples and for solving optimization problems. I'll also show you something at some point of time. Okay. So, yeah, that's about the modeling exercises. And one announcement I want to make is when you answer, like people are answering questions and stuff. So just say your name when you speak, because I don't know who is talking, and many times my screen is shared, so it's like navigating back to the chat box becomes a bit hard. So just say your name when you ask a question. Okay. So, okay. Let me just share my screen. Okay, so yeah, still okay. I think it should be visible now, right? The screen is visible.
Yes, ma'am, it is.
Okay. Okay, so there's one thing I wanted to just highlight. In the last class, we were looking at this vertex cover problem, right? Like the security guards example, where you wanted to position guards at different vertices of a graph. And we wrote a formulation. So that was a vertex cover formulation. And one of you mentioned about this formulation. Okay, just give me a minute. For some reason it's not opening. Okay, so one formulation that someone suggested was this, like you had something of this form, such that xi plus xj is strictly greater than 0 for all ij in the graph, something of this form, right? And we had it was a 0-1 program, it was an integer program. So remember that I was telling you, like, try to avoid these kind of constraints which have this, the issue is this, Okay, it's a strict inequality. So instead of that, you can put something like this: xi plus xj is greater than 1, greater than or equal to 1 for all ij. Okay, so when you start modeling some problems, you should keep this in mind, that you should either bring it in inequalities of strict, of greater than or equal to or less than or equal to. You should avoid the strict inequalities, or you can have equalities. So some constraints of this form, like xi plus say xi xj equal to 0. This kind of a thing is okay. Okay, equalities and greater than or equal to, less than or equal to, these kinds are fine. So why this becomes a problem is, for instance, like let me consider this problem. Okay, so let's say minimize x such that x strictly greater than 5. Okay, so can someone tell me what is the answer to this? I want the minimum value of x such that x is strictly greater than 5. So,
Ma'am, there is no answer.
5.00001.
so one person said there is no answer. So the two options, no answer for this. So who said this?
Ma'am, Siddharth Shah.
Siddharth Shah. Okay. And somebody said 5 point.
Ma'am, Rohit here. 5 point,
Yeah.
basically lots of zeros, 1. If it is a real value, if it is an integer, then 6.
Okay. Okay. So I don't have any integer constraints here. So it's all in the continuous domain. So yeah, there are two options here. Okay. So now if I fix this, so let me come to this option, answer to what Rohit said. So if I look at this one, like 5 point, a lot of zeros and 1. Now if I take one more 0 and make it 1 here, that is still a feasible point, right? It's greater than 5. It's strictly greater than 5. And it's the objective is less than this value, right? So you can keep going on and on. So there is really, there is no end to it. Okay, so that's the kind of numerical issue. So, but intuitively, like you think it should be 5, but when you code this up on any solver, they won't know. The solvers don't know how to solve something like this. So the answer is yes. It's no answer. So there's this problem. There is no minimum, but the infimum is what we refer to as infimum. That is 5 here. Okay, so I'll come to defining infimum and those notions. So this is a numerical issue that comes up. So that's the reason why you avoid these kind of strict inequalities. Okay, so just keep that in mind when you try out some of these modeling assignments. All right, so yeah, so let me now get into the next topic. Like I wanted to cover some of the preliminaries which are needed for this course. So some preliminaries in linear algebra and some in calculus. Okay, so this document that I'm showing you, it's just for my purposes so that I can, run this classroom. So it's in no way a complete set. So you have to go through some of the standard linear algebra textbooks and also calculus textbooks, okay, for this. So let's just start. So here we'll look at vectors and matrices with real valued entries for this whole course. So in general, you can look at vectors and matrices with complex entries and so on, but that's not going to be the focus in this course. Okay, so yeah, I think you all have done a linear algebra course, but just a brush up. So if you look at a set of vectors, v1 to vm, a linear combination is something of this form, right? It's summation ci vi, so where ci's can be anything in the real line. Okay. Yeah, ci is again c. These kind of issues will be there in this, so because it's just to help me with the flow of the class. So ci's are all reals. Okay, and so it's just some this is called a linear combination of the vectors. Okay, so it's basically you do a scalar multiplication with these ci's and then sum them up. That's what is a linear combination. Okay, now next is this notion of linear independence. So when do we say a set of vectors is linearly independent? So what you're trying to convey here is that, you cannot write one in terms of a combination of the other. Okay, so to capture this, mathematically, this is the way it's done. So you try to write this combination, summation Ci Vi is 0, and this is if you can write this way, it means that all the Ci's have to be 0. Okay, even if you can write it in a way that one of the Ci's is non-zero, then it means that they're linearly dependent. Okay, so to see this example, you can take this one. Okay, so 3 vectors 1 2 3 1 1 3 and 0 1 0. So what is a combination? So if I write summation Ci Vi equals 0, what is the value of Ci I get? So you should write C1 times 1 2 3 plus C2 times 1 1 3 plus C3 times 0 1 0. Okay. So if I say this is 0, right? So what is the value of C1, C2, and C3? So of course, C1, C2, C3, 0 gives you this, but is there any other value you can put for C1, C2, and C3? Okay, so anybody wants to try?
Ma'am, 1 minus 1 and minus 1.
Yeah, so 1 minus 1 and this one is what? 1, right? Minus 1.
Yeah.
Okay. So so basically this vector is the difference between these two. Right? So that's how you can express one in terms of the other. So that means this is linear. This is a linearly dependent set of vectors. Okay. Now, if the given vectors includes this 0 vector, then by default it becomes linearly dependent, right? So if I add plus zeros, okay, so I can add anything. So maybe some 5. So I can add some, say, C4 here, and C4 can take any value, right? So that becomes a linearly dependent set. Okay, so remember that a linearly independent set cannot contain the 0 vector. Now, now this is an example of a linearly independent set. You could try to, solve and see if you can fit any value of, C's other than 0, which satisfies this. Okay. Yeah. Now coming to span of vectors. Okay, so the set of vectors, it's a span for some set. Okay, so if any vector in this set S, you can write it as a linear combination of these. Okay, so the set S is called a span of these V1 to Vn. Okay, and also V1 to Vn are said to span the set S. Okay, so basically you can write it in this form. You can write any vector V in S as this form. Okay, so yeah, okay, so I think this is kind of obvious for all. Now, what is a subspace? So a set of vectors is a subspace in Rn if you have these two properties, right? So if any scalar multiplication you take, it gives you something in the set. Okay, and if you take an addition of these vectors, that is also going to give you something in the set. So the idea is that basically any linear combinations you take, that's going to give you the same set. It's that linear combination of those vectors will lie in the same set. Okay, so such a set is called a subspace. Okay, so an example is this. So you're given this vector A is given. So now you have the set of all vectors X such that A transpose X is 0. Okay, so then this is a subspace. This set S, this is the set S. Okay, and that is a subspace. So you should try to verify that these properties are indeed satisfied. Okay, so just a quick one is, so if X lies in this set, now if you take some alpha X, so you'll also get this lies in the set, right? Because you know that A transpose X is in the set because A transpose X is 0 because it lies in the set. Now if you take A transpose alpha X, so that will also be 0. Okay, so that's why this is a subspace. Now, a small change in this definition here, if it is instead of equal to, if you put it as greater than or equal to, so this is what is called a half space. So, but this is not a subspace. Okay, so you can try to see where it fails. Okay, one of these two properties is going to fail. So, can somebody tell me which property is going to fail here?
The scalar multiplication property.
And why is that?
Because if we multiply with the negative numbers, then the sign will get
Sign will
reversed.
change. Exactly. Okay, so so that's why this is not a subspace. Okay, now there are some other subspaces which are important here. You would have learned these in linear algebra. These are null spaces and range spaces. So these are very important as far as matrices are concerned. So if you're given a matrix A, which is of size Rm cross n, which is of size m cross n, and it's a matrix of reals, then the null space, you define it by the set of all vectors such that Ax is 0. Okay, so the matrix A transforms these vectors in the null space to the 0 vector. Okay, so this is called the null space of this matrix, and this is a subspace. Okay, so remember, so all these x's have to be in Rn. Okay, so that's why the null space of A is a subspace in Rn. Okay, now another space that we have is the range space. So this is the set of all x's which you can write as A times some w. Okay, so AW for some w. If you can write it in this form, then this x belongs to what is called the range space. Okay, so this, if you see, so w is in Rn, right, and AW is going to be something in Rm. Okay, so this one is Rn, and here you're going to get something in Rm. Okay, so that's why the range space of A is a subspace in Rn. Okay, so so let me just write it here. So suppose these are the columns of A. So here you have A1 and A. So this is A. Yeah, the first column basically, second column, and so on. So when you multiply this with some W, what you're going to get, so this is W1, W2, and so on up to Wn. Okay, and here you have up to An. So what this product is going to give you is a linear combination of the columns of A. So it's going to be summation Wi Ai, where Ai is the ith column of A. Okay, so so that's where this is going to be in Rn, sorry. So yeah. So this quantity is as big as, I mean, the dimension is the number of, the size of the columns, right? Yeah. So, yeah. Sorry, I think I said something wrong. So this is as big as, how many rows you have here. So this is going to be n. So each of these AIs is in Rn. Okay, and these are all scalars. And so that's why this combination that is going to give you something in Rm. And so this collection range space of the matrix A is a subspace in Rm. Okay, so these are important subspaces, and you should verify that these are indeed subspaces. Okay, now when we say basis for a subspace, so this is a set of vectors that you can use to construct the subspace in all. Okay, and so that you take some linear combination of these, you will get back the whole subspace. You won't get anything more than the subspace. Okay, and you indeed get the whole subspace. So that's the idea of basis. Okay, so the notion of linearly independent is required to ensure that there's nothing redundant. Okay, so V1 to Vn have to be linearly independent. If not, what you can do is you can remove some of these vectors, because some of them are redundant, as you can express them in terms of a combination of the others. So, so the idea is to have the smallest collection of vectors which together will span the space S. Okay, so that's the idea of a basis. And this number, the number of vectors which are required in the basis, that is called the dimension. Okay, so in this case, the dimension is n. Okay, now if So one thing to note is if you know that a vector space has dimension m, then if you take any collection of more than m vectors, then you will get a linearly dependent set. Okay, so yeah, a linearly independent set has to be something less than m vectors, less than or equal to m, and more than that, if you take, you're surely going to get a dependent set. Okay, so I think these are things you would have learned, right, in your linear algebra class. Yes, no?
Briefly, ma'am.
Briefly? Okay. So you're familiar with null spaces and range spaces, right?
Ma'am, if you could quickly recap those, that would be great. Rohit here, by the way.
Okay. So yeah, so null space is just, like I said, it just takes everything to 0. Anything like you multiply ax equals 0 and the set of all these vectors x. Okay, that's what is going to give you the null space. Okay, and range space is just the linear combination of the columns of A. Okay, so that is the range space. Now, sorry. Yeah, so coming to, like, okay, you can find the basis of all these vectors, the null space and range space. But before that, if you look at the dimension, okay, so okay, so if you look at, so the way to do this is you have to find the set of linearly independent collection. So if you look at the range space, so what you need to do is, everything in the range space, you can get it by the columns of A. Because after all, it's a collection of it's a collection of linear combinations of all the columns of A. Okay, so so yeah, at least you know where to look in order to get a basis. So it should be these columns of A. Now the thing is, some of them may be redundant. They may be like you can express one in terms of the other. So the way to do that is you eliminate which of them. Like if you keep like the first one alone, if you take A1, so that is just one vector, and yeah, as long as it's not zeros, that is a linearly independent set. Now you bring in A2. So now you have A1, A2, and you see if this is a linearly independent collection. Okay, if yes, go ahead, and otherwise you remove A2. And so you keep on doing this till you cover all the n columns. So that's the principle of this basis. So whatever you're left with finally is going to be a basis for the range space. Okay, so it turns out that yeah, so whatever you're left with is the basis, and the size of that is called the dimension. Okay, so this dimension has some some particular properties, especially for when you define it for matrices. So the dimension of the range space is the same as the dimension of the column space. Okay, so yeah, so you can also define another notion, right, in terms of the rows of A. So you have A1, you have A2. Suppose you have now the rows. So there are m rows of the matrix, and now you can define something in terms of linear combinations of these. Okay, so for all the rows. So here this is going to give you another space. This is called the column space. Okay, sorry, this is called the row space. Okay, I think I messed up some of the definitions. Sorry. Okay, so column space is what I just said, like the linear combinations of the columns. So that's also called the range space. Now this is called the row space. Okay, so there's a unique property that the dimension of the row space is the same as the dimension of the column space, and that is what is called the rank of A. Okay, so this is actually how you get this is the number of linearly independent rows of A, or the number of linearly independent columns of A. So if you are not familiar with this, like you should go back and check some of your linear algebra concepts. So you can check this textbook by Gilbert Strang for this. Okay, so this is about the dimension of these various spaces. Now, similarly, you can also define the dimension of the null space. So this is the collection of vectors which such that x set of all x such that x is 0. Okay, and so in the same manner, you can construct a basis here, and the dimension of that basis is called nullity. Okay, now in order to construct the basis, another thing that's often used is called the Gauss elimination scheme. Okay, so it's for finding the solutions to this Ax equals 0, and those solutions will in turn give you an idea of the subspace. Okay, and they'll also give you an idea of the basis. Okay? So these are some things, if you are not comfortable, you have to go and just practice how to compute these subspaces. Okay. So yeah, so now coming to inner products. So I will try to, okay, for this basis, let me see if possible, I'll try to illustrate it later. So now coming to inner products, I think inner products you are familiar with it. So it's a product of these two vectors x, y, and it should satisfy these. So it's written in this way. Okay, this angular notation is what is used to describe an inner product, and the inner product of x and x, if you take, it's always greater than 0. Okay, and it's equal to 0 only if x is the 0 vector. And it has these properties which you want, like symmetry. So if you take this operator with xy and yx, you're going to get the same thing. And you have this property where you can add up inner products to get an overall inner product. Okay. And scalar multiplication. If you multiply x with r and you take the inner product with y, okay, so that, okay, I don't know why I wrote this. So yeah, this is going to be something like r outside. Okay, so r, if you take outside and you just multiply x and y together, that's going to be giving you the same values. And if r is complex, if you want to bring this r down to y, then you need to take its conjugate. Okay, so these are some of the properties of inner product, and anything that satisfies these kind of properties is called an inner product. Okay, so the common inner products you would have seen is, one is this vector multiplication, right? When we write x transpose y or summation xi yi. So this is a very commonly used inner product. And alternate representation for this is of this form, where you write norm x, norm y, cos theta, and the theta is the angle between the vectors. So if you write this is x and this is y, and we have the angle between them is theta. So the length of this is what we'll refer to as norms. I'll come to norms in a little while. So you have norm x, that's the length of this, and norm y, which is the length of this vector. And the inner product is just xy cos theta. Okay. So this is something you would have seen in your, I think your 12th standard time, and perhaps even after you joined for undergrad. Okay, so some things of this inner product, some properties are like, because it depends on this cos theta. So if x and y make an acute angle, if an angle less than 90, then this inner product is positive, because cos theta is positive, and these values, the length, these are lengths, and these are always going to be positive. Okay, positive or non-zero, basically. Yeah, non-negative rather. Okay, so if the, okay, now, so if you have an angle, like an obtuse angle, so between 90 and 180 degrees, so something like this, okay, then the inner product is negative. So this angle is an obtuse angle. So this cos theta is going to be a negative value, and so you're going to get a negative value for the inner product. Okay, now for when exactly you have 90 degrees. Okay, so in this case, the inner product is 0. Okay, so that's when you say the two vectors are orthogonal. Okay, so the two vectors are orthogonal if x transpose y is 0. Okay, and additionally, if you also have that the length of these vectors is 1, then they are orthonormal. Okay, So this thing of norm, right? This is something I will come to in some time, but here we are talking of the usual sense of norm, which we say as this, right? X1 square plus X2 square plus so on. So this is the norm of X in this case, okay? Now, in terms of some of the subspaces that you saw, okay, so you have this null space of A, then range of A transpose, and so on. Okay, so here also there's this orthogonal notion that comes in. So the null space of A and the range space of A transpose. Okay, so let's just see how that comes up. So null space of A is a set of all vectors such that Ax is 0. Okay, so now range space of A transpose, right? It's basically, it's all the columns of A transpose if you take. So this is A. So all the columns of A transpose means the rows of A. Okay, so this is, okay, so I'll just write it in words. It's the linear combination of all rows of A. Okay. So now, just by definition, right, these two spaces are orthogonal, right? Because the null space of A, so how did you get that? So you took each row of A, and if you multiply it with X, you're going to get 0. So each row of A and X, if you take, the dot product is 0, or the inner product is 0, and they're orthogonal, okay? So that's why these two spaces are orthogonal. Okay. Now, similarly, you could show it the other way: the null space of A transpose and range space of A. It's just, you can just try it for yourself. It's just symmetric in this way. Okay. So now, if you're given any collection V1 to Vm, so yeah, at start that may not be an orthogonal set, or it may not be an orthonormal set. Now, this Gramschmidt orthogonalization process helps you to transform this into a set of vectors W1, say up to Wm, okay, such that Wi transpose Wj is 0. Okay, so this, if you're not familiar with, you should try to read this up. So the idea is just simple. So you start with V1. Okay, now V1, as such, it's this is one vector in the collection, so there's no notion of orthogonality. So you can just make it an orthonormal set by, just dividing it by its norm. Okay. Now the next vector you take, V2. So it will have a component possibly in the direction of V1, right? So this is V2 and you have V1. So it will have one component along this direction and one component in the orthogonal direction. Okay, you can decompose it in that way. So the idea is to remove everything in the component of V1 so that you're left with an orthogonal only this direction. Okay, so that's the idea. And so that will get transformed to some W2. Now, next, when you take V3, you will remove everything in the direction of W1. So this was the direction of W1 itself, because you just did a scaling. And for W2 was actually this one. Okay, and so W3, for V3, when it comes, what you need to do is remove the components in the direction of W1 and in the direction of W2. And what you're left with is called W3. And it should also be normalized to have a length 1. Okay, so this is the idea of this Gramschmidt orthogonalization process. So this will be relevant at a later point when we look at some of these algorithms, the conjugate gradient algorithms specifically. So if you're not familiar with it, you should just go and revise this. Okay. Now, this rank nullity theorem, this is another really important theorem in linear algebra. What it says is that the rank of A. So rank of A, if you remember, it's basically this, right? It's the number of linearly independent columns or the number of linearly independent rows of A. Okay, so the rank of A plus the null, the dimension of the null space, that will give you the number of columns of A. Okay, so yeah, just to get some intuition of this. So this whole thing is N, right? And actually, yeah, you have everything in Rn. Okay, that is your overall vector space. And in this, there are some of them which are in the null space, and there are some of them which are in the it's in the column space of A. Okay, sorry, not yeah, should be the row space because it's Rn, right? Yeah. So there's some of them in the row space, and there's some which are in the null space. Okay, so remember that these are two orthogonal spaces. So you saw here, right? So just this point here that we had about the null space and the range space of A transpose. So this is actually the row space. So these are two different components, and together you will, if you combine them, then you can get something in Rn. So what I mean by combining is if you take some vector in Rn, so it is possible to write it as a sum of two parts. Okay, so you can write it as x, let's say xna plus x R A transpose. So what I mean by this is this xna lies in the null space of A, and this x R A transpose lies in this space, this range of A transpose, or it's lies in the span of the rows of A. Okay, so that's intuitively what the rank nullity theorem signifies. Okay, so any questions till this point? You're all very quiet. Is there something you want more clarification on?
No.
Okay. See, you guys have to speak up. Otherwise, I can't see your faces, or I don't know what's going on. So, if something is unclear, please stop me. Okay. I'm kind of rushing through this because I think at some point you would have possibly seen these concepts. So I think all of you have done a linear algebra course, right? So the idea is you must have seen this at some point. Of course, of course, you would forget things. If it's been some time and all that. But anyway, like you have some time to brush these topics up. Okay, so this is just to bring you back in this frame. Okay, so please stop me if something is unclear. Okay. And there's really no problem if you have forgotten also. So don't worry if you have forgotten. There is, you can just bring it back. Okay. Okay. So, yeah. So one thing is, some of these concepts, it's like all over the place. So it's I told you about this notion of AX, right? And I said how you can get this product. So one way is like okay, let me just say the way that you have been familiar. I already mentioned it briefly, but maybe some more insights into how you multiply matrices. Okay, so the usual notion of multiplication is probably you would have seen like to multiply these two, let's say this matrix and this vector, what you would do is you would multiply the first row with this column. Okay, so 1 times 0, 2 times 1, and 3 times 0, so that gives you 2. Now, then you go to the second row times this column. Okay, and so that will give you 5, and so on. Okay, so if you have multiple columns here, then you again repeat this action for all the columns. That's how you get the entire matrix, the product. Okay, now another way to do it, a simpler way, is to do it using just the columns of this matrix. So actually, this product, it's same as doing 0 times 147 plus 1 times 258 plus 0 times 369. Okay, so this is another way to multiply matrices, a matrix by vector. Okay, so each entry of this column vector you take and you multiply with this column. So first you multiply with this, then you take this element and multiply with this. Now you take this element and multiply with this. Okay. So this is probably a faster way to multiply, because see, if you have a lot of zeros, then immediately now you can just read off the answer from here. So it's only the second column that you should take. Okay, so actually every column of this product is a linear combination of the columns of A in that sense. So this is a linear combination, right, of the columns of A. So now that is one other way you can use. Now another way is to do it as a linear combination of the rows of B. Okay, so here, yeah, maybe you don't have a very complicated thing, but maybe something like, yeah, let's maybe just show it here itself. So, so just take 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and suppose you have yeah, 0, 1, 0 only. Let's take. So to get this one other way, this is the method 2 here. So the first method is probably what you might have been seeing, like a dot product of the rows and the columns. This is as a linear combination of columns, and this is method 3 as a linear combination of the rows. So that what it means is you take the first row, okay, and it's going to be 1 times, so if this is A and this is B, 1 times the first row of B, okay, plus 2 times the second row of B, plus 3 times the third row of B. Okay, so this is going to be the very first row of this product. Now, if you want to get the second row of this product, you now look at this row of A. So this will be 4 times first row of B plus 5 times the second row plus this quantity 6 times the third row of B. Okay, so similarly, you can fill up the last one. Can somebody tell me? Can someone answer this? What's the last row of this AB in terms of, you know, the rows of B?
Seven times the first row of B.
7
Plus
times first row of B, right?
8 times the second row of B.
8 times the second row of B.
And 9 times the third row.
Right, yeah, 9 times the third row. Okay, so yeah, so this is now 3 ways you have to multiply matrices. So, you know, you can use them, you know, depending on the particular situation. Sometimes one of them will be easier than the other and so on. And more than the computational speed, it helps to have this view of matrix multiplication. So this immediately tells you that this product is going to be something in the column space of A. So it's going to be something as a linear combination of the columns of A. So something in the column space you get. Now here, if you take, you're going to get something in the row space of B. Okay, because it's a linear combination of the rows of B. Okay, so this is an important view to have. So you can try now, like, you know, just try to multiply some matrices and try these different methods to see that you really get the same answer. Okay, so next thing I wanted to do was to getting to this thing of solution of the system Ax equals B, but I guess we are kind of close to it's almost 11:17, so 2-3 minutes only. So maybe this is something I can teach you tomorrow. So any questions so far?
No, ma'am.
Okay, so I think I see the same people answering, so I want to hear also from some of the others. So I'm glad that you guys are answering, so please continue answering. But what about the others? I want to know if things are all fine. So anybody from the third year class, like BTech third years, what do you feel? Is it going okay? Are things clear or something needs more clarity? Is anyone here from the BTech third year class?
Yes, ma'am. And it's clear right now.
It's clear, okay.
Yeah,
Good.
okay, also, ma'am.
Okay. And what about the fourth years? Someone from fourth years? Anyone here? Fourth years are very quiet. There is no one here or what? Okay. Okay. So I think they choose to remain silent for some reason, but please open up in case things are not clear. What about the master's students? Things are okay so far?
Yes, ma'am.
Okay. Okay, so maybe I will stop with this for today and just brush up some of these topics from any standard linear algebra textbook if this has been fast so far. Okay, so I'll meet you all tomorrow, Friday at 2 p.m. Okay, so thanks a lot.
Thank you, ma'am. Thank you, ma'am.
Good morning, ma'am.
Yeah, hi, Venkatesh.
Yeah, ma'am.
Maybe we'll just wait for a little while so that everyone
sure, ma'am.
leaves, maybe just a few seconds. I'll also just stop the recording. And then
Okay, ma'am.